Another category of unsupervised techniques in machine learning is dimensionality reduction. Usually your data are very high dimensional. For instance, if you have images, the number of pixels in an image is going to be your dimension. So even if your images are 32 by 32, which is very low resolution, you're going to have a vector that is 1024 dimensional. So the idea of dimensionality reduction is to look at the dimensions that are the most important in your data. Now, what do I mean by most important? How do you define importance for a high dimensional vector, for a high dimensional data set? The importance could come from the variance. So you look at your data, this is the original data in the original coordinate system. This is your data point. It has this feature, petal length, and this is petal width, for instance. Okay, it's in the original coordinate system. The idea of principal component analysis is to come up with another coordinate system. So rather than using the Euclidean coordinate system, let's just do another coordinate system. And what we want is that each axis in this coordinate system is explaining most of the variance in the data. So in this dimension, your data have a lot of variance. In this other dimension, the variance is less, but still there is a significant amount of variance. Maybe your data is three-dimensional, and then you're gonna come up with another dimension that's pointing out of our screen now, and that one is less important. So we are sorting our coordinate system according to their importance. And the importance, measure of importance, is the amount of variance in the data that each axis is explaining. Okay, so this axis is explaining most of the variance. This is the second most, etc. That's how you measure importance. Why do they call it components? Because these are your components. These are your new coordinate system. And then the principal, because these are the most important ones. Now, if you have a 1024 dimensional vector, perhaps you can look at the first 10 components, and that's explaining the most of the variance in your data, most of the variation in the data. And the rest of it is just small variations you can ignore, okay? And I don't want to go into the details of the math, but I want to give you an idea of what type of courses you need to take in the future to understand these methods. We know that the variance matters, actually the covariance matters. So we are going to create a covariance matrix. And then to compute these vectors, we are going to look at the eigenvectors. So V is an eigenvector in this direction and in the other direction. And lambda is an eigenvalue. And where are you going to learn about these? They're going to be in your linear algebra courses. So a major course for data science is linear algebra. It's extremely important. And another one is probability. You need to understand what is a probability and etc. What is a normal distribution, what is a binomial distribution, etc. So linear algebra is very important. And that's actually how you're going to compute your principal components. Let's say an example. We know that iris data, except for the labels, is a four-dimensional vector. We can do principal component analysis. We are going to center the data and scale it, which basically means we are subtracting the mean and divided by the standard deviation. We can look at the summary, and these are our principal components. The first component is explaining 72% of the variance in the data. The second component is explaining 22% of the variance in the data. The third component is explaining only 3% of the data. And this is just 0.5% of the variance in the data. So they are being sorted according to their importance. And let's just borrow some plotting tool. And this is exactly what I just explained. The first component is 72% important. The second component is 22. The third component is less important, and the fourth component is the least important. What does it mean? We can take our data and we can project it into these two dimensions, the first two. Now you can take a look at your data in principal component 1, principal component 2. These are most of the variance in your data, and it's a good technique for visualizing your data. We know that our data probably has one cluster here. It is mingled here, And this is a nice way to visualize your data. This could be 1000 dimensional data, but then you can plot it in 2 dimensions or 3 dimensions.